to this morning session of our ISSI-BJ on Things to Come webinars. We have today Professor Cheng, which that I would like to thank for accepting our invitation. You can see him in the webcam. He's in the US right now, and therefore, given the time difference, it's 9 p.m. there for him, and it's 9 a.m. here for us, while our webinars are usually in the afternoon. But thank you very much once again for being here after the holidays. And in the webcam, you can also see Professor Ip, who is the Executive Director of ISSI-BJ. If it's not your first time listening to our On Things to Come webinars, then you know what it is about and you know about ISSI-BJ. But if you don't, and if it's the first time, I'm going to say a couple of words before we can start with the lecture. So ISSI-BJ is the International Space Science Institute Beijing, which was established in 2013 thanks to the collaboration between the National Space Science Center of the Chinese Academy of Sciences and the International Space Science Institute in Switzerland, in Bern. And since then, we have organized plenty of activities and events, including forums, workshops. We have international teams, we have working groups, and of course, given the current situation, we had to switch to online activities instead of offline ones. And therefore, last year in September, we've started this On Things to Come webinar series that aims to introduce ongoing and new and future space missions. And therefore, we invite outstanding scientists to present them to the public. And thus, we have today Professor Cheng, who is going to talk about the DART mission, but I won't say too much about him because I will ask Professor Ip to introduce him to you. Thank you very much for being here once again, and hope you enjoyed the webinar.
Yeah, thank you, Lola. So everybody, good morning, and good evening, Andy. So today we have Professor Andy Cheng to give a talk on the very interesting mission of NASA, the DART mission, and he will describe to you later. But I want to say a few words about Professor Andy Cheng himself. Andy was he did his undergrad at Princeton, and he went on to Columbia to do his PhD under the famous Professor Marvin Ludeman. Is that right?
Yes.
And I remember his origin, he studied as funny things like pulsar, neutron star, like that.
Yes. A long time ago.
but then he switched to metaspheric physics, for his good judgment. And I remember that, at that time, at one time, I would say, Professor Alex Dessler was talking to a number of us. And he said, "Oh, because at that time there was an interesting discovery. I remember it was a kind of like a theta aura, if some of you still remember. And for a long time, no one could explain it. So Alex would talk to us and say, "Hey, you guys, please come up with some idea. You guys have no idea. This would be like Andy Cheng." Oh, I want to take a hole to hide.
Oh, Alex, yeah.
So Andy, you make trouble for us,
I know, I'm in big trouble. After all these years, someone remembers.
Okay, but then the Andy he went to work at APL very early, right? I think in 1983.
Yes.
But then since then he had a brilliant career there. In the middle of it, he was deputy chief scientist of NASA, and I don't know what you did there, but you were a deputy chief scientist. Great. And he was involved in a number of very impressive missions of NASA, including the near mission to Eros, right? The first mission for a spacecraft to land on an asteroid. And he was an interdisciplinary scientist on the Galileo mission, and he was involved in Cassini and then involved in Hayabusa. But then today he's working as the project scientist for the DART mission, which I think would be a very, 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 very interesting one because it has many things besides the study of the asteroid itself, which is a binary system. and also have a lot of significance on the Earth defense, I suppose, right?
Mhm.
And it's so important that the ESA is joining in on July 21st. Later on, Mikhail Kupers will be talking about the Hera mission, the CubeSat mission in company with your mission. Okay, Andy, we are going to listen to you. Thank you so much.
Okay, so thank you. It is a great honor to be speaking to you. And let me start sharing my screen if I remember how. Okay. All right, so I'm talking about the double asteroid redirection test. That is, I will call DART. We are 7 months to launch. And you can see if anyone wishes to contact me by email or also by phone, I'll give you a phone number if you like. Just do that. And we have a picture of the DART spacecraft. It's heading for the moon of the binary system called Didymos. And DART is a demonstration of asteroid deflection, changing the orbit of an asteroid by running a spacecraft into it. So this is about, as Professor Ip mentioned, it's about planetary defense. So mitigation of the asteroid impact hazard on Earth. Asteroids are always hitting the Earth. Small ones do so very commonly. And in fact, we have in the map here, a global map, fireballs seen from space, where the color code is the impact energy, where the largest impact seen since the time period, the 12-year time period, 32-year time period shown is the famous impact over Chelyabinsk in Siberia, Russia. This was an approximate 20-meter object. The impact energy is the size of a small atomic bomb, 500 kilotons TNT, but it was an airburst. And it caused damage on the ground. It caused over 1,500 injuries to people, but mostly broken glass, minor damage to buildings, that kind of thing. There are, of course, larger impacts that occur less commonly. There's a famous impact over Tunguska, also Siberia, which was a roughly 5 megaton impact. It destroyed the area like a city-sized area, a few thousand square kilometers. This type of, the Tunguska impact occurred in 1908, and the impact of this size occurs every several hundred years, 300 years or more. Then, of course, there's a famous impacts like the one over Chicxulub in the Yucatan. It's over here. That was the end of the Cretaceous period. It was the Cretaceous Tertiary boundary event 65 million years ago. This was a 10 or 15 kilometer object, an impact every few hundred million years. So it's a mitigation of asteroid impacts. So the question is, suppose someday we discover an asteroid that will impact the Earth. What can we do? That was the question. What can we do? So planetary defense is the problem of trying to understand what we can do. We want to assess, of course, the problem. There are many aspects to this problem, and this is a diagram that's shown by the NASA Planetary Defense Coordination Office. We want to find the objects, we want to understand the threat, we want to understand what kind of damage and impact is likely to cause, so you can plan, you can decide whether you need to mitigate or not. But DART is the first NASA mission that actually is a full-scale demonstration of a technology to deflect an asteroid, meaning change its orbit. And so someday that may prevent an asteroid from hitting the Earth. That would be a very good thing if we could do it. So the DART mission is about doing the demonstration of how you can take a spacecraft, fly it into an asteroid, and change the orbit. And as Professor Ip also mentioned, DART is part of an international collaboration called AIDA. This is with the European Space Agency and the Hera mission. So you will hear about the Hera mission, I gather, shortly. This is a mission that will launch in 2026, I believe. No, 2024, arrive in 2026. And we'll go to the same system, and we'll study the effects also of the DART impact. So DART actually is shown here. DART will impact the moon Dimorphos of the binary system Didymos. I will explain why we want to do that shortly. DART will carry a CubeSat called Licia Cube. Licia Cube is provided by the Italian Space Agency, ISSI, that's Italy. So there is an international agreement between the US government and Italian government so that DART will carry Licia Cube to the target, and Licia Cube will separately fly by the asteroid and image the effects of the DART impact. I'll talk a little bit more about that. But the DART and Licia Cube together with Hera will carry, as it turns out, also two CubeSats. They're called Milani is one of the CubeSats, Juventas is the other CubeSat. Those are the two CubeSats that will be carried by Hera. Hera has, of course, instruments on its own. They will also be studying the Didymos system. I will say a little bit more about Hera as well. Okay, so back to DART. As I mentioned, DART carries Licia Cube. DART is an approximate 600 kilogram impact onto the moon Didymos at about the impact speed is between 6 and 7 kilometers per second. The actual impact speed varies according to exactly what day we launch, but starting off 6.2 going up to close to 7. There will be Earth-based observations, and the impact date is September 26 is the first, and it goes up to the first week of October. Again, the impact date also changes depending exactly what day we launch. All right. But DART will target the binary asteroid Didymos. It will impact the moon of Didymos, and the result of the DART impact will be to change the orbit of the moon around the primary. And specifically, it will change the orbit period. The change in the orbit period is measured by ground-based telescopes. It turns out that as seen from Earth, the Didymos system is an eclipsing binary. What that means is that the two bodies move in front of one another as seen from Earth, so that the moon either is eclipsed by or casts a shadow on the primary. As a result, if you monitor the light curve, you have mutual events, and by timing the mutual events, you can make an accurate determination of the period. This period will change when DART hits it, and that is how DART will confirm that it hit the target, change the orbit, and actually measure the amount of the orbit change. Okay, so what is DART supposed to do? As I mentioned, DART will impact the moon, specifically during the close approach of the Didymos system. The Didymos system comes within 0.007 AU from Earth in October of 2022. That's an extremely close approach. It does not get that close again for another 40 years. So that's an exceptionally good opportunity to observe Didymos. By impacting the moon, DART will change the binary orbit period. Change it by enough, it will measure the orbit period with ground-based telescopes. And the fourth activity also is to understand what happened, and specifically to measure the momentum enhancement factor, which I will talk about more. But basically, the amount of momentum that you transfer to the target in the impact is greater than the incident momentum of the spacecraft. And you get this enhancement because the impact makes a crater, and there's crater ejecta. The crater ejecta carry off momentum as well. And so there's a recoil of the target body with greater momentum than the spacecraft brought in. Essentially, what's happening is the crater acts like a little rocket engine, and it pushes the target away so as to increase the amount of momentum that's transferred in the impact. So this is now a sketch of the spacecraft running into Didymos. You can see the arrows that we're planning a head-on collision. The result of this collision is that the orbit semi-major axis changes a little bit, it goes down. So Didymos, so the moon Dimorphos drops closer to Didymos. The orbit period gets shorter. The orbit period gets shorter, and that's what we will measure. What is the advantage of the binary asteroid? The binary asteroid allows a detectable deflection of the asteroid of relevant size. Relevant size meaning, I haven't told you the sizes yet. Dimorphos is a 160-meter object. DART is not a large spacecraft. It's a 500-kilogram dry mass. It's not a. It's a smallish spacecraft. The DART impact will change the orbit period of Dimorphos by about 1%. It's a 10-minute orbit change, period change. 10 minutes is easy to measure in the telescope. That's about 1% change, and that's detectable in a matter of several weeks. Should be easy to detect. If you ask yourself, what was the change in the heliocentric orbit, the orbit of the system around the sun? That is very tiny. And the reason, of course, is that the heliocentric orbit velocity is so much larger. I'm creating the same delta V, the same change in the speed, but that's only a tiny fraction of the orbital speed around the sun. And the result, as you could see, the change in the heliocentric orbit is really, really tiny. So the advantage of doing this test at a binary system is that we have a much larger effect. We can measure it from the ground. That's very important because that means the DART is a standalone mission. With one spacecraft, we can do the deflection, and we can also measure the effect, and we can learn something about how the asteroid responds to the kinetic impact with one spacecraft. Whereas if we wanted to measure the change in the heliocentric orbit, you would need another spacecraft in rendezvous with the system in order to be able to measure that tiny effect. And even then, it's a very difficult measurement to make. And, well, extremely difficult measurement to make. Let me just leave it at that. A little bit to show you some pictures of the DART spacecraft. I've already mentioned its maximum wet mass, not to exceed 676 kilograms. It's carrying also some technology demonstrations. One of them is the so-called NEXT-C. This is a NASA evolutionary xenon thruster. So it's an ion engine. Because it has an ion engine, it also has huge arrays, solar arrays. These are a new kind of solar array, first flight in deep space for these solar arrays, which roll out. You see that this is how they are rolled up. These are roll-out solar arrays. So these are the dimensions of DART. It's about a 2-meter box, but the arrays, wingtip to wingtip, it's almost 20 meters. So it's enormous. I think it's not large compared to the space station or commercial, ComSats, but it's enormous for a small science spacecraft like DART. Okay, so I already mentioned the ion propulsion engine. I will be talking a little bit later about the autonomous navigation. In order to be able to actually hit a target as small as Dimorphos, the 150-meter target, in order to be able to hit that, it needs to guide itself. So autonomous navigation using a camera as this camera, it's 8-inch, 200 millimeter aperture f/13 camera. I mentioned the solar arrays, ion engine. CubeSat I will talk about. This is from Italy. It has a planar antenna. Planar antenna is nice. It packs nicely within your spacecraft. Also flying a new solar array technology with flexible concentrators. Okay, so let's talk a little bit about DART targeting Dimorphos. So this is a timeline, 30 days, 10 days, 8 hours, and so on. So talking the early time, first detection in the camera of the Didymos system is about 30 days out, we're predicting. And we have continuous ground coverage. This is from the NASA Deep Space Network, starting 10 days out. But the autonomous navigation will be enabled about 8 hours out. At that point, Didymos is unresolved. It's still a point source. And starting about 4 hours in is when the spacecraft will actually start controlling itself. Approximately 1 hour out is when you cannot really see in this image, but that's approximately when the target, the actual target, can actually be resolved from the primary. And so that's actually one of the interesting challenges of the autonomous targeting in this case, is that there are two targets in the system, and the brighter one is not the one we want to hit. We want to hit the moon, not the big guy. So anyway, so over the last hour is when the system decides which target is the right target, locking in, and then heading toward it. In the final 4 minutes, these are simulations of what the image would look like. In the final 2 minutes, the larger moon actually moving out of the field of view of the camera should be locked in, putting the target at the center. And it's only in the last 20 seconds that we're close enough to the target that we are meeting the science requirements for the resolution. We want to know very accurately where the dark impact is. We want to understand what kind of terrain it hit, whether we're on boulders, whether there are boulders nearby, whether it's a smooth area. Also, what was the slope of the surface where we hit? Is it a normal impact, an oblique impact, so on. We need to understand all these things. And the pixel scale requirements, we want to be better than meter per pixel. That's a very short time before DART actually hits. So that's one of the great technical challenges of the mission also, is that we have only a very short time to get the most important data. And it's not only just acquiring the data, it has to be transmitted back to Earth before the spacecraft hits the asteroid. And that's the end of, well, obviously that's the end of the spacecraft activities. So 20-second. So basically during this entire period, DART is transmitting data at the maximum rate that can be accepted. We're maximizing the throughput into the NASA Deep Space Network. So the limit is actually set by NASA. That's the fastest that NASA can receive and transmit and handle any data. So the 3 million symbols per second. So 3 megahertz, I would just say. So that's our maximum data rate. We push them up to that limit, and that's the data rate at which DART is transmitting image data back to Earth. And requirement is that within actually the last image to be returned within the final 7 seconds before impact, and that you're talking about 10 or 20 centimeter per pixel images of most of the target. So that's the main thing that the Draco camera will be up to. So let me change topic a little bit. How are we doing? Okay, I'm doing okay. Talking about the little bit of science, the problem is momentum transfer efficiency. Some of you, if you've been interested in the question of how to deflect an asteroid, you've been exposed, you've seen diagrams like the one I have on the left. We bring in an incident momentum. You have an enhanced momentum transfer. You have ejecta. Because there are ejecta coming back at you, the momentum you transfer is bigger than the momentum you bring in, and the ratio of the two is called beta. It is the final momentum. It's the momentum you transfer to the target divided by the momentum input. And if you have no ejecta, beta is 1. You do have ejecta, and so beta and the ejecta are in the backward direction, so there's beta is increased. Okay, so this is a familiar concept. It's been discussed for decades. To apply to DART, however, we immediately realized that this formulation that you see has to be, well, we have to ask ourselves, how does this work in 3D? The reason being that the incident momentum and the enhanced momentum transfer, the ejector, they're not collinear vectors. This is not a one-dimensional problem, it's a three-dimensional problem. Especially if you actually hit a target, but you don't hit it exactly in the center, and the target may not be actually in a sphere, right? It's an irregularly shaped body, and we may not hit exactly in the center. What is the normal? The surface normal is not in the same direction as the incident momentum. Okay, so the more general formulation looks exactly the same basic idea here, but you write momentum conservation. You have the final, the momentum transfer, the change in the momentum is the sum of the incident momentum, that's what this term is with the U, the incident momentum, and then the ejecta momentum. So these are just two scalar numbers. And the vector n. This is a unit vector, which is the direction of the net momentum of ejecta. So it's the ejecta momentum direction. And it's easy to show from this that beta is the transferred momentum component along this vector n divided by the incident momentum component along this vector n. So that is the appropriate generalization to 3D. We choose to do this instead of pretending, I mean, alternatively, you could just write beta as a tensor. We don't want to do that. We would prefer to have beta as a scalar number and have in the definition of beta these two additional vectors, the direction of the incident momentum and the direction of the ejecta. Actually, there's two, the way it's written here, it's three vectors, but they are related by the momentum balance, so there's really only two independent vectors. So that's the definition of beta here. And if you have a smooth surface and your incident momentum is not too far off the local surface normal, so it's not a very oblique impact, meaning that if it's within something like 40 or 45 degrees of the surface normal, your incident projectile direction, then it's close enough to normal. If it's close enough to normal and the surface is smooth enough, it's not very bouldery, it's not got very fine topography, then the vector n, we just know from cratering experiments, also crater simulations, that the vector n, the direction of the ejecta momentum, is, to very good approximation, it's given by the local target surface normal. So you'll find this in the literature that n is the surface normal, but that involves a few assumptions. They may work for DART or they may not. If we remember what the pictures of, some of you may have seen what the Hayabusa 2 found at Ryugu, also what OSIRIS-REx mission found at Bennu, that you may have a very bouldery surface, and then there's even a question how you would define appropriately what the surface normal would be if you're trying to impact that. Well, anyway, so from the basic momentum equation, the n here, this vector that appears in the definition of beta, it's the ejecta momentum direction. Okay, so let me say a little bit about, so DART, how does it measure beta? Okay, many things. One point to make is that DART measures a period change in the Didymos binary. Period change in the Didymos binary measures only one component of the velocity change. Velocity change is a vector, it's three components. DART only measures one of them because it measures the period change, the orbit period change. DART does not have a way of measuring the inclination change, the eccentricity change. Okay, Hera will come along and measure inclination after the impact and eccentricity after the impact, but we do not have measurements before the impact. Okay, so DART will also use, DART has several working groups. DART has over 100 scientists already working or working with or on the investigation team. full two-body numerical modeling of the Didymos binary dynamics. We need to do this because, let me just quickly go back and remind you, the Didymos system looks sort of like this. It's not two spheres, and it's not tiny masses in a large variety. This is rough. This is not even to scale. The separation between the two bodies is 1.8 kilometer. It's only 1,800 meters. I should have shown you the Dimorphos size. Dimorphos is about half the height of the Eiffel Tower. The Eiffel Tower in Paris is only twice as high as the size of Dimorphos. And so this is 1.8 kilometers from one body to the other. The size of Dimorphos is an 800-meter sized body. So these guys are very large and they're very irregular. What that means is that the system does not exactly obey Kepler's laws because these are not spherical bodies. And in fact, the motion is non-Keplerian at the 1% level. So the deviation from, say, Kepler's third law to determine the masses of the bodies is around 1%. We hope to do better than that in our measurements. What that means is that you have to use full two-body numerical modeling. What that means is we have to do detailed numerical model accounting for the shapes of the bodies. Now, the shapes of the bodies are not that well known currently, but we expect that they will become very well known after we get there. But we have to use that even to be able to relate the semi-major axis of the system, I say a mean semi-major axis of the system, to the mass. You would think, oh, Kepler's law should do that. And so, well, yeah, Kepler's law do that, but only to about 1% accuracy. If you want to do a more accurate determination of what the mass and system is and so on, we need to do full two-body. It couples also the orbital motion to the spin, and we have to take into account the tidal interactions. It turns out we have a dynamics group, and they've been studying all these things. It is really fascinating. Okay, I mentioned mass here because if you ask yourself, how do you determine a momentum transfer? There's two things. You've got to measure a velocity change, and you've got to measure a mass. Those two together give you a momentum change, okay? We don't know either of those now. I already mentioned to you that the direct measurement of the period change is only one component of the velocity. We have to use the full two-body modeling to be able to say something about the other two components of the velocity change that we did not measure. And then we have to relate that to the system mass. Okay, now DART will measure the size, shape, and volume of the target. And we have an idea of what the bulk density of the system is, but well, again, in order to do that, really, to determine the total mass of the system, we will need to use the full two-body numerical modeling. We'll have to make assumptions too. For instance, that the density of the two bodies is the same. Is that so, or is that not so? Well, we won't know for sure until actually Hera arrives in the system. Hera will arrive in the system in 2026. Hera will directly measure the separate masses of Dimorphos and Didymos. We also know from the DART terminal imaging where the impact was and what the impact site looked like. And that's important because we want to get an idea of what the ejecta momentum direction n is. What is the local surface normal, and what does the surface look like? We're doing detailed impact simulations. Numericals, that's another one of our large working groups involving, in all cases actually, involving investigators from both the US and from Europe and around the world, even also outside of Europe, to account for what are the effects of the spacecraft geometry. This is the spacecraft geometry not being a simple sphere, the effects of the impact site topography, boulders, etc., and also to understand what are the uncertainties. Lichia Cube I will talk about in more detail. The Lichia Cube is going to be taking pictures right after the impact. It's going to directly image the ejecta plume. And so we'll be able to say something about what is the direction of that plume. That's going to be very important. And also by measuring the time evolution of the plume, it would be able to, for instance, determine whether you have a gravity-controlled or a strength-controlled crater. The time scales for the plume evolution are very different in those two cases, and also the nature of the kind of evolution, what kind of crater you make and what the ejecta plume look like, both depend on those target properties, whether it's strength or gravity control. If it's gravity control, it means it's so weak that the growth of the crater and the ejection of material from the body is limited ultimately by the gravity of the body instead of by the strength of the material. Okay, so let me change subject a little bit, talk about the where we are. We're about the integration and test. Integration and test started back in April 2020 with the delivery of the ION engine, which you see there inside its cover. And the spacecraft was integrated with a side-by-side arrangement. So most of the boxes are on panels. The panels are first integrated separately, but on the panels, with the whole spacecraft opened up. The propulsion system and the spacecraft core structure come as a separate unit. So the spacecraft has both a chemical, hydrazine, monopropellant propulsion system in addition to its ion engine. So it's solar electric xenon propellant system, xenon tanks, and the hydrazine tanks are all inside the central tube here. There's an integrated electronics, it's called, APL calls it CoreSat. Just recently completed in the months February, March of this year, just recently completed the spacecraft level thermal vacuum testing. That was successful. The solar arrays, these are roll-up solar arrays. This is when they're extended. So obviously they have done a number of deployments of these arrays, the testing of the deployments, both at cold temperature and at room temperature. So this is during one of these or after one of these deployment tests. Both solar arrays are delivered already. They are at APL. They are delivered. They are now being integrated on the spacecraft, actually currently this week being integrated. The telescope is not yet delivered, but there were some issues in development, so it was late. And in fact, it's the telescope being late is the primary reason why DART had to move to its secondary launch period. Secondary launch period begins in November 2021. But the telescope has now been rebuilt, and it is just completed its realignment, and we'll be starting the vibration test next week. Next week, starting vibration testing. So we are hopeful that the telescope delivery, anyways, it's planned for June, then spacecraft vibration and shock testing in July, pre-ship review. It will be launched out of Vandenberg. This is in California on the US West Coast, not in Florida, but on the California. Launch in October. It's shipping to there, and opening of the launch window is November 24 in 2021. Okay, let me change topics a little bit, talk about LichioCube. LichioCube is built by an company, Argotec, in Italy, in Milan, actually. And it is provided by the Italian Space Agency. And there's a team of scientists led by Elisabetta Dotto. You may know her. She is at the National Observatory in Italy, in Rome, INAF. And the Italian science team has a number of universities, University of Milan, University of Bologna. Okay. So the idea, LichioCube is carried by DART. It's actually part of DART. It's released by DART 10 days before the DART impact. It has its own propulsion system. So it separates from DART. It has to establish a slightly different trajectory, because if it did not, it would impact Didymos along with DART. Okay, we don't want that. So it separates from DART, has its own little rocket engine, its own propulsion system, and so it will execute a separate flyby of Didymos about 3 minutes after the DART impact. So DART hits first, and then LITCHICube flies by, and LITCHICube uses its cameras, 2 cameras, and will be taking pictures of the impact, taking pictures of the impact plume, tracking the asteroid as it flies by. And then after the impact, it turns around. This is very important. It also images the side of the asteroid that DART is not able to see. Of course, DART only sees one side because it then hits the asteroid. It never sees the other side. But LITCHICube will see the other side. So that's very important. LITCHICube afterwards returns the images directly to Earth. So these are some of the goals of LITCHICube. It's imaging the impact plume, imaging the impact site, or at least around the impact area, and imaging the non-impact hemisphere, the side of Dimorphos that is not seen by DART. The fields of view of the 2 cameras are large enough that actually it will see both targets. So that both cameras have large enough field of view that it will see both objects, both Dimorphos and Didymos. So the non-impact hemisphere of both objects. I maybe should mention that LITCHICube is actually based on the Argo Moon CubeSat, which was to fly to the moon on another US mission, the so-called EM1 mission, its first flight of SLS. In 2020, it said, unfortunately, of course, that did not happen. It's now going to be 2021. But anyway, so the first flight of Argo Moon, which was supposed to be DART, never mind. Anyway, Argo Moon and LITCHICube are essentially the same design. So these are the 2 cameras. Okay, so I've already mentioned there's a DART impact. Then LITCHICube will look at the ejecta. LITCHICube will make high-resolution images. The highest resolution imaging of the target will be about 1.4 meter per pixel from LITCHICube, and then imaging the backside, the non-impact hemisphere, and then looking at the plume and forward scattering. So very exciting data set. Let me say a little bit also about Hera. Hera and DART, of course, are part of AIDA. And Hera makes a very important contribution because it will directly measure the mass of Dimorphos. That's the other half of the story. I mean, DART will have a pretty good idea of what the 3-dimensional velocity, even though it measures only one component, but with the velocity change, with the numerical simulation, we have a pretty good idea of what the other 2 components will be. So the mass of Dimorphos is going to be a question that will be measured directly by Hera. So that's a very important thing. The other very important measurement Hera will make, of course, is to measure the DART impact crater. How big is it? How deep is it? So again, that's very important information to tell us more about the nature of the target. To combine that with especially powerful to combine that with the LITCHICube observations of the impact plume. And the third thing Hera can do that's really exciting is to study these very interesting dynamical changes that will occur in the Didymos system. One of the things that we believe the Didymos system now should be a dynamically relaxed system, meaning that the libration should be minimal, only a few degrees, maybe much less than that even. The orbit may even be circularized, in which case it may be tidally locked. We don't know yet. Hera will see, of course, after DART hits it. When DART hits Didymos and changes the orbit velocity of the target, it will also have the effect of exciting spin of the moon, as well as changing the eccentricity and the inclination of the orbit. The result is that the librations after the impact may be, well, certainly will be significant and measurable by Hera, may be large enough, depending on exactly what the shape of Didymos is, and also depending on how large the momentum transfer is, and where DART hits, all these issues, it's possible that Didymos will not only have large amplitude vibrations, but may even be turned into a tumbling state. So one of the very exciting possibilities that Hera can study is this dynamical state. So changes, possibly dramatic changes in the spin state of the target, understanding what they are and why that happens. And by looking at these things, it's possible that you can infer the moments of inertia of the moon. So basically constraining its internal structure. It's also the question we have been asking is whether we will be able to see any evidence of the tidal damping of the system. It's something that we're arguing about and trying to simulate and understand. Very interesting. We, of course, to the next bullet, both the U.S., both the international observational teams, of course, plans to continue the telescopic observations of Didymos, even after the DART impact, of course, probably going out at least through the Hera impact, because you want to continually monitor the light curve and see whether these changes, there is an issue. An issue is that some of the DART ejecta, if there's ejecta at low velocity, and if you have a gravity-dominated crater and a very weak target, there's a lot of mass ejected at low velocities, and even a significant fraction of the total ejecta mass may be left in temporary orbits in the system. So you create a ring, if you like, or a disk. If that happens, which is possible, it's maybe even likely, then the light curves will be very interesting to monitor over that whole time to see the evolution of these temporarily orbiting or disk-like material. That's one possibility that'd be interesting to study in telescopes. The other interesting possibility is that the ejecta escape and create a dust tail like in a comet. So it's basically, it's turning Didymos into an active body. And so it's an artificially, it's like a main belt comet. It's these activated asteroids. Didymos will become one. And we've done some estimates of the brightness of the dust tail. Is quite possible. In fact, it's likely that these extended dust tails will be able to be imaged by ground-based telescopes. Probably only large telescopes, but that's also a very interesting possibility. Basically Didymos turning into an active asteroid after the DART impact. And of course, the simulations trying to understand all of these, trying to predict, help us try to better be able to predict what the outcome of a future kinetic impact might be, and also help us determine beta. And what is the range of possible beta values that we have with Hera data? Well, before Hera data, because Hera data, we have to wait 4 years to get it, but after Hera data as well. And then there's the modeling of the dynamic system, the dynamical modeling of this binary system. It's incredibly rich and complicated. And we're seeing that it's exquisitely sensitive to the detailed shapes and interior mass distributions of the body. So this is a rich problem, and I suspect people are going to be working on it for a long time to come. So I'm almost done here. So DART is the first demonstration of planetary defense capability. So the most important thing about DART, we shouldn't forget, it's just showing that we can actually deflect an asteroid with a kinetic impactor. And so this demonstrating also technology set. So most importantly, the autonomous navigation. You can hit an asteroid that small, you can hit it the right way to cause an orbit deflection. How you do that? Okay. The determination of the momentum transfer efficiency. There's a lot of argument in the literature. I don't know if you've followed. But how much momentum do you transfer? I haven't mentioned numbers for what we think beta is, but they range all the way down from very close to 1 to very large values, so more than 5. And there are laboratory experiments done with, small, centimeter scale targets up to even meter scale targets. People have done experiments to try to measure beta. And in the meter scale targets, we have measured beta values of around 2. Okay, these are rocky targets. I don't know. Okay. So anyway, DART will measure or determine a momentum transfer efficiency for a target body, 160 meter size. I haven't talked about it very much, but that is the representative size of the threat. It's the most likely threat of an impactor, as in the recent, if you were participating in the recent Planetary Defense Conference exercise, in fact, their target was about the same size as the DART target. It is the most likely threat. And the DART target, the Didymos, is S-type, which is the most common spectral type in the near-Earth population. And one of the important outcomes is that we do want to be able to better understand and predict what a future kinetic impact will do if you ever have to deflect another asteroid. So we need to improve and validate the models. So we need to understand what happens when a kinetic impactor hits an asteroid, and we need to be able to model it. So the models are an important outcome of the DART impact. Okay, so I guess I am finished and happy to discuss, have questions, answer any questions people may have.
Many thanks, Professor Cheng, for the outstanding presentation. There are, in fact, some questions, but I would like to still encourage listeners to on Bilibili and also here to ask more. The first question is, how big will the ejecta be?
How big? I'm not sure. Okay, you mean the size of the impact crater or the ejecta particles? We have no information. Okay, I'll answer both. The size of the crater depends on the nature of the target. It could be as small as 3 or 4 meters for a very strong target, up to a few tens of meters for a very weak target that is either in or close to the gravity regime. In terms of the particle size, we have prejudices, I would say. We have no actual information. If the Didymos target is like the targets that have been visited by Hayabusa 2, and OSIRIS-REx, then the regolith on the bodies is very coarse, meaning it's only large particles, or very few of the fine particles. So basically nothing smaller than a few millimeters, maybe, if it's like Itokawa, although there are dust coatings on all these particles, the dust coatings consisting of micron size or even smaller dust. The particle size where most of the mass is in the ejecta is millimeter size and up, we think.
Thank you.
Maybe not.
And
we'll find out.
Thank you. Would some of them hit the spacecraft?
Okay, DART, of course, will hit the moon before, so it's not, the question is not relevant to DART, but the question is relevant to LiCiaCube. And LiCiaCube has designed its trajectory to avoid hitting any of the ejecta. And it has a closest approach distance, I did not mention, of more than 50 kilometers away from the body, and also a time delay after the DART impact of almost 3 minutes. And the idea is to be far enough away from the target that none of the ejecta, even the fastest ejecta you expect, which is moving at a few hundred or several hundred meters per second even, they cannot reach the, basically avoid hitting any of the ejecta particles. So the trajectory is designed to avoid that, given a model of what the fastest ejecta would be.
Thank you very much. Could the impact change the rotation period of the target?
Okay, the impact is on the moon, Dimorphos, and will certainly change the rotation period of the target. I think I've been trying to say that. How that change, what that change looks like is something we do not know. It depends not only on where DART hits the target, exactly where the impact point is, through the center or an edge or whatever. It also depends on the shape of the body. And it turns out when you model it in detail, it depends on everything else in the system as well, even the rotation phase of the primary and the shape of the primary, because these are all spin orbit coupled. So yes, the impact will change the rotation period of the target. And how much of an effect, that's why we need to do the full 2D modeling of the system.
Thank you. Next question is, would you end the mission by landing or smashing one of or more of the CubeSats on the surface of Didymos?
Okay. Actually, that's a very good question to ask Mikhail Kuplers when he talks to you about Hera, because I believe the Hera team, they are discussing doing things like that. But that's yes, it's a question for him. DART, of course, will hit the moon, and that's the end of DART, a very sudden and decisive finish. Lichia Cube will fly by, and after the flyby, of course, Lichia has to downlink all of the images back to Earth. So Lichia Cube has to live for another month or so to be able to downlink the data. And then it's in a heliocentric orbit, and it will not go to any other place.
Thank you. Next question is, so far the last one is, will there be a follow-up mission or missions to the DART project?
A specific follow-up to DART, no. However, the NASA Planetary Defense Coordination Office, the NASA office, the Planetary Defense Office has a full program, Planetary Defense Program. And so that program will continue to fly more missions. So yeah, in that sense, yes, there will be follow-up missions. I don't know what you exactly mean by follow-up mission to DART. So the NASA Planetary Defense Program continues, so there will be more NASA Planetary Defense missions. The next mission, however, we don't know what exactly it would be. It may be the search mission, the NEO-SM search mission.
So there are other questions, from the audience. If you do, please unmute yourself and ask the question.
I can't see so far any further question. If you have any, I'm talking to the audience. Please ask in the chat box, because we still have less than 5 minutes, so time is now. If not, as it seems, I would like to thank once again Professor Cheng for, again, the excellent presentation.
One more question did come in.
Oh, yeah. Will you measure the electromagnetic environment?
Yes, sadly, you mentioned the space physics. No, we do not. And I believe Hera has a dust experiment, but it does not have a electromagnetic measurement, and there's no magnetometer. Hera will carry a radar, but it's a ground penetrating radar.
Okay.
Rola, maybe you could announce the next talk the follow-up talk by Mikhail Kuplers.
Yes. We will have a talk on the Hera mission, actually, with Michael Kuppers, and it will be on the 21st of July. It's not the upcoming talk, because the upcoming one will be with Professor Robert Pappalardo on the NASA Europa Clipper, and it will be on the 12th of May, so next week. But again, Professor Cheng mentioned the Hera mission several times, and we will have a talk about that one too in July. If there is no further question, and if Professor Cheng and Professor Ip allow that, I would like then to end this webinar, this excellent webinar. Thank you once again, Professor Cheng, and thanks everyone for joining the webinar today, even though the time was a bit different. But hope you enjoyed. And again, we have recorded it, so we will publish the recording today or tomorrow, and it will be available on YouTube and Bilibili. Thank you very much.
Thank you so much. Andy, thank you.
Thank you also
Bye-bye.
for
Good night.
joining me.
Yeah.
Good night.
Thank you.
Good night.
Good night.